Hello, everyone. Welcome to today's session. I'm excited to introduce you to our topic, Physics Chapter 1, Units and Dimensions. This presentation is brought to you by Varun Vijay. We will explore the complete concept of units and dimensions, including examples, dimensional formulas, tricks, and exercises to help you understand better. So let's get started and dive into the fascinating world of physics. Let's take a closer look at what this chapter covers. We start with the concept of physical quantities, which are the measurable properties of physical systems, like length, mass, and time. Understanding these is essential because they form the foundation of all measurements. Next, we discuss systems of units, which are standardized ways to express these quantities consistently across different contexts. This naturally leads us into fundamental and derived quantities. Fundamental quantities are the basic ones, like length, mass, and time, which are independent. Derived quantities, on the other hand, are combinations of these, such as velocity or force. We then move on to the SI system, or the International System of Units, which is the globally accepted standard. It includes the base units for fundamental quantities, ensuring consistency worldwide. After that, we explore dimensions and dimensional formulas. These are powerful tools that help us analyze physical quantities by expressing them in terms of fundamental dimensions, making it easier to check the correctness of equations. Following that, we look at applications of dimensional analysis, which is a method for simplifying problems, deriving relationships, and checking the validity of equations without detailed calculations. We also have a list of important dimensional formulas, which serve as quick references for common quantities and their dimensional expressions. To solidify understanding, we will go through some examples and exercises, applying these concepts practically to enhance our grasp. And finally, this material is prepared by Varun Vijay, whose insights will guide us through these fundamental ideas with clarity. Let's start by understanding what a physical quantity actually is. A physical quantity is essentially a measurable property of matter. It helps us describe and quantify different aspects of the physical world around us. Now, every physical quantity can be expressed as a numerical value multiplied by a unit. For example, if I say 10 meters, that means I have a numerical value of 10, and the unit is meters. This combination allows us to communicate measurements clearly and precisely. It's important to recognize that there are different types of physical quantities. Some have only magnitude, which we call scalar quantities. Others have both magnitude and direction, known as vector quantities. Understanding these distinctions is fundamental as we explore the broader concepts of measurement and how physical quantities form the basis of scientific analysis. This slide lays the groundwork for appreciating how we quantify and interpret the physical properties of matter. Let's take a look at the different systems of units used in science and engineering. First, we have the CGS system, which stands for centimeters, grams, and seconds. This system is primarily used in fields like physics and chemistry. Then, there's the MKS system, where the units are meters, kilograms, and seconds. MKS is quite common and forms the basis for the SI system. Speaking of which, the SI system, or the International System of Units, also uses meters, kilograms, and seconds. The key point here is that SI is essentially the MKS system used globally, making it the standard for scientific measurements worldwide. Lastly, there's the FPS system, which is used mainly in some engineering fields, especially in the United States, with feet, pounds, and seconds. Understanding these systems helps us communicate measurements accurately across different regions and disciplines, which is essential for clear and consistent scientific work. Let's take a closer look at the fundamental quantities that form the basis of our understanding of physical measurements. First, we have length, which is measured in meters, abbreviated as m. This is the most basic dimension we use to describe the size of objects and distances. Next is mass, measured in kilograms or kg, which tells us how much matter is contained in an object. Then there's time, measured in seconds or s, which helps us understand durations and the sequence of events. Moving on, we have electric current, measured in amperes, or A, which is essential when studying electrical phenomena. Temperature is another key quantity, measured in Kelvin, abbreviated as K, and it indicates the thermal state of a system. We also consider luminous intensity, measured in candela, or seed, which is important for understanding light and brightness. Lastly, the amount of substance, measured in moles or mol, helps us quantify the number of particles, atoms, or molecules present. All these quantities are fundamental because they serve as the building blocks for all scientific measurements and calculations. They are interconnected and essential for developing a consistent framework to describe our physical universe. Remember, these quantities are standardized, ensuring that measurements are consistent everywhere in the world, which is crucial for scientific progress. Let's take a closer look at what we call derived quantities. These are concepts like force, pressure, energy, power, velocity, acceleration, and momentum. What's important to understand is that these are not fundamental quantities themselves, but rather combinations of the fundamental quantities we discussed earlier. For example, force is derived from mass and acceleration, while pressure comes from force acting over an area. Energy and power relate to work done and the rate at which work is done, respectively. Velocity and acceleration describe how an object moves and changes its motion. These derived quantities help us describe physical phenomena more comprehensively and connect to real-world applications. They form the bridge between basic measurements and complex systems, making our understanding more practical and complete. Remember, this concept of derived quantities is fundamental because it shows how different basic measurements come together to describe the world around us more effectively. And as we move forward, keep in mind that understanding these relationships is key to mastering physics and engineering principles. Let's delve into the concept of dimensions and dimensional formulas. Essentially, physical quantities can be expressed in terms of fundamental quantities like mass, length, and time. The general form is physical quantity equals m raised to the power of a, l raised to the power of b, and t raised to the power of c. For example, consider force. Its dimensional formula is written as m1l1t2. Here's a trick to find these exponents easily. First, write down the formula of the physical quantity, then replace each term with m, l, or t, and finally, identify the exponents for each. This method simplifies understanding how different quantities relate to the basic dimensions. Remember, this approach helps us analyze and compare physical quantities systematically, which is fundamental in understanding their relationships and in solving various physics problems. This concept, developed by Varun Vijay, is a crucial foundation in dimensional analysis. Let's take a closer look at some important dimensional formulas in mechanics. These formulas help us understand the fundamental nature of physical quantities by expressing them in terms of mass, length, and time. Starting with velocity, its dimensional formula is m0l1t. Notice here that mass doesn't play a role in velocity, which makes sense because velocity is about how fast an object moves, not how heavy it is. Next, we have acceleration, which has the formula m0l1t2. Again, no mass factor, but time is squared in the denominator because acceleration measures how velocity changes over time. Moving on to force, its dimensional formula is m1l1t2. This is crucial because force depends directly on mass and acceleration, which is reflected here. This formula is foundational in Newton's second law. Now, work and energy share the same dimensional formula, m1l2t2. This indicates that energy involves both mass and the square of length, divided by time squared, aligning with the work done when a force moves an object over a distance. Power, which is the rate at which work is done, has the formula m1l2t3. Notice how it adds an extra t compared to energy, representing the division by time. Then we have momentum, expressed as m1l1t, which combines mass and velocity, emphasizing how momentum depends on both the object's mass and its motion. Finally, pressure is represented by m1lt2. This negative exponent for length indicates force distributed over an area, which is exactly what pressure is, force per unit area. All these formulas are vital because they provide a consistent way to analyze and compare different physical quantities in mechanics. Remember, understanding these fundamental dimensions helps us derive equations and check the correctness of our calculations. And a quick note, this content was put together by Varun Vijay, and it forms a core part of grasping the mechanics principles we'll build upon throughout the course. Let's take a closer look at some important dimensional formulas related to heat and thermodynamics. First, we have energy, or heat, which has the dimensional formula of m1L2T2. This essentially tells us that energy depends on mass, length, and time in this particular way, reflecting how energy scales in physical systems. Next, we have specific heat, which has the dimensional formula of m0L2T2K. Notice that the mass dimension is 0 here, indicating that specific heat doesn't depend on mass directly, but relates to how much energy is needed to change the temperature of a unit mass per degree Kelvin. Then, there's the gas constant R with the same dimensional formula as specific heat, m1L2T2K. This makes sense because the gas constant links energy and temperature in thermodynamics, so their dimensional relationships are closely connected. Finally, we have Boltzmann's constant, which shares this same dimensional formula, as it plays a fundamental role in connecting microscopic properties with macroscopic thermodynamic quantities, emphasizing the deep link between energy, temperature, and the underlying particle behavior. All these formulas are crucial because they help us understand how different physical quantities relate dimensionally, which is essential when deriving equations and ensuring our models are consistent. And of course, all of this ties back to the overall theme of understanding heat and thermodynamics at a fundamental level. Let's take a closer look at some important dimensional formulas related to electricity. These formulas help us understand the fundamental nature of electrical quantities by expressing them in terms of basic physical dimensions. Starting with charge, denoted as Q, its dimensional formula is m0L0T1A1. This tells us that charge is fundamentally linked to the unit of current, since it has a dimension in terms of current, but no mass or length dimension. Next, we have potential, or voltage, represented as V. Its formula is m1L2T3. This indicates that voltage relates to energy per unit charge, and we can see that it involves mass, length, and time dimensions, as well as an inverse relationship with current. Moving on to resistance, R, its dimensional formula is m1L2T3A2. Resistance depends on how difficult it is for charge to flow, which connects to these fundamental dimensions, especially involving the square of current's inverse, highlighting its dependence on material properties and geometry. Now, capacitance, C, is expressed as mL2T4A2. Capacitance measures how much charge a capacitor can store per unit voltage, and its dimensional formula reflects that inverse relationship with mass and length, but a quadratic relationship with current. Then, magnetic flux, letter 3D5, has the dimensional formula m1L2T2. This quantity relates to magnetic fields and the amount of magnetic field passing through a given area, involving energy and magnetic properties. Following that, we have inductance, L, which is given by m1L2T2A2. Inductance describes how a circuit opposes changes in current, and its dimensions are similar to magnetic flux, but with an emphasis on the current's squared inverse. Throughout this slide, what's most important to grasp is how each electrical quantity can be broken down into fundamental dimensions. This helps us analyze and relate different electrical phenomena in a consistent, scientific way. Remember, these formulas are crucial for understanding the physical nature behind the electrical concepts we study in this course. Let's take a closer look at some important dimensional formulas related to optics and modern physics. First, we have frequency, which has the dimensional formula of m0L0T. This essentially means it depends solely on time, representing how many cycles occur per second. Next is wavelength, with a dimensional formula of m0L1T0, indicating that it depends on length, which makes sense because wavelength is a physical length of a wave. Then we have the refractive index, which is dimensionless. With the formula m0L0T0, this tells us it's a ratio of two speeds or lengths, so it doesn't have any units. Moving on, Planck's constant, denoted by h, has the dimensional formula m1L2T. This is a fundamental constant linking energy and frequency, so its dimensions reflect energy times time. Next is the gravitational constant, g, with dimensions mL3T2. This constant appears in the law of gravitation, describing the strength of gravity. Notice its unique dimensional dependence, especially the negative power of mass, indicating its inverse relation to mass. Finally, surface tension has the dimensional formula m1T2, which makes sense because it involves force per unit length, reflecting the energy required to increase the surface area of a liquid. All these formulas help us understand the fundamental physical quantities and how they relate dimensionally. Remember, these dimensional analyses are crucial in verifying equations and understanding the physical nature of these constants. Thanks to Varun Vijay for compiling this essential information to deepen our grasp of optics and modern physics concepts. Now, let's explore some key applications of dimensional analysis. First, it helps us check the correctness of a formula. By ensuring that the dimensions on both sides of an equation match, we can verify if the formula makes sense physically. Second, it allows us to derive relationships between different quantities. When we understand the dimensions involved, we can often find new connections or simplify complex formulas. Third, dimensional analysis is very useful for converting units from one system to another, making sure our calculations are consistent across different measurement systems. For example, if we look at the kinetic energy formula, Ke equals half times m times v squared, we can check its dimensional formula as m1L2T2 and confirm that it's correct. This process is essential in ensuring our equations are dimensionally consistent. Remember, these applications are fundamental tools that support us in developing accurate and reliable physical models. This slide is brought to you by Varun Vijay. Let's look at some practical examples to understand dimensions better. First, for pressure, the dimension is m1L2T. This makes sense because pressure is force per unit area, and force itself has the dimension of mass times acceleration. Next, for energy, the dimension is m1L2T2. Energy relates to work done, which involves force and displacement, so its dimensions reflect that relationship. Finally, checking the equation F equals ma, the dimensions of force are m1L1T2, which confirms that mass times acceleration correctly gives force. These examples are really helpful because they show how we can verify and derive the dimensions of physical quantities. Remember, understanding these fundamental dimensions not only helps in solving problems, but also in ensuring our equations are dimensionally consistent. This ties back to the overall theme of our presentation, the importance of dimensional analysis in physics and engineering. And as always, it's essential to connect these concepts to real-world applications to see their true significance. Let's go through some exercise questions to reinforce our understanding of the concepts. First, we're asked to write the SI units for force, pressure, and power. Remember, the SI unit for force is the Newton, for pressure it's the Pascal, and for power it's the Watt. These units are fundamental in expressing these physical quantities consistently. Next, we need to find the dimension of surface tension. Think of surface tension as force per unit length, so its dimension involves force divided by length. This helps us understand how surface tension behaves dimensionally compared to other quantities. Then, we're asked which quantity has the same dimension as energy. Remember, energy and work have the same dimensions, which are mass times length squared divided by time squared. Recognizing this helps us connect different physical quantities through their dimensions. Moving on, we have to convert 1 Newton into dynes. Since 1 Newton equals 10 dynes, it's a straightforward conversion, but important to remember for unit consistency in various contexts. Finally, we need to check if the equation S equals ut plus half it squared is dimensionally correct. This is a fundamental kinematic equation, and when we analyze its dimensions, we find that both sides are consistent, confirming its correctness dimensionally. These exercises are designed to strengthen your grasp of units, dimensions, and the fundamental relationships between physical quantities. Keep these concepts in mind as they form the backbone of understanding physics deeply. Let's take a moment to look at some useful tricks and short notes related to dimensional analysis. First, we have force, which is expressed as m1L1T2. This indicates that force depends on mass, length, and time in this particular way. Next, work is represented as m1L2T2. Notice how it involves the same mass and time factors as force, but the length dimension is squared here, reflecting the idea of work being force applied over a distance. Moving on to power, which is m1L2T3. Power is essentially the rate at which work is done, so it includes an extra factor of time in the denominator, indicating how quickly work is performed. Then, pressure is given as m1Lt2. This tells us that pressure relates to force distributed over an area, which is why length is to the power of -1. Finally, g, the gravitational constant, is expressed as mL3T2. This one often trips people up, but remember, it relates to the force of gravity and how it acts over distances. And here's a nice quote to keep in mind. Jitni Zayata practice, utna easy dimensional concept. The more you practice these, the easier they become. This is a great tip from Varun Vijay, our book writer, emphasizing that consistent practice makes mastering these concepts much simpler. So, keep practicing, and these dimensional tricks will become second nature. Now, let's wrap up with a quick summary and motivation. Units are fundamental because they measure physical quantities, giving us a standard way to express and compare things like length, mass, and time. Dimensions, on the other hand, help us understand how these units relate to each other and provide a deeper insight into the physical relationships involved. There are 7 base units in the SI system, and these serve as the building blocks for all other units we use in science and engineering. Using dimensions, we can verify the correctness of formulas, ensuring that the equations we derive or use make physical sense. And as a final thought, I want to leave you with a quote. Physics isn't just about memorizing formulas, it's about understanding the relations between physical quantities. That understanding is what truly drives progress and innovation. This perspective really ties everything we've discussed together and highlights the importance of grasping the underlying concepts, not just the equations.